seminar of Prague. We are delighted to have as guest Alexander Stottmeister from ITP Hannover, and he will tell us about the construction of real-time local quantum fields in 1+1 dimensions. Please take it away.
Okay, well, thanks again for the invitation. So, yeah, I don't know, maybe some of you might have seen a similar talk already, depending on what kind of online seminars you're listening to. So what I want to report on, and this title was already said, is work with Daniela Cadamuro, Tobias Osborne, Vincenzo Morinelli, Gerardo Mosella, and Jota Nimoto, which have all contributed to various aspects of this project, and we are working on extending the models we can discuss in this setup. So the outline of the talk will be that I first give some brief motivation and context, so what kind of structures we're talking about. Then I will present a method which I call operator-algebraic renormalization, which is a formulation of Wilson-Kadanoff renormalization in terms of operator algebras. And then to keep it kind of hands-on and simple, I will tell you how this works in the case of the transverse field easing model, which is a kind of 1+1 dimensional version of the classical 2-dimensional easing model. And yeah, if I have time, I can also tell you something about how to reconstruct conformal symmetries and the disorder parameter in this context, and also how it might be relevant to quantum simulation of quantum field theory, which is kind of a topic we are also working on in Hannover. So for the first point, so motivation and the context, so kind of overarching goal of this program, if you want, is that we want to have a construction or approximation of quantum field theories in real time, so not Euclidean imaginary time framework or even conformal field theories as more specific ones, via lattice models. And the main reason here is that, well, the construction approximation aspect covers this aforementioned mathematical implementation of Wilson-Kadanoff renormalization group in quantum field theory. And in that context, quantum field theories and conformal field theories arise as or via so-called RG fixed points, so fixed points of the renormalization group. And there's this usual duality of either using them to understand short distance physics, especially via the construction of quantum field theories in the continuum, or that you view these things as being related to long distance physics, where you talk about continuous phase transitions in condensed matter systems. And the specific construction via lattice models is motivated by this simulation aspect on quantum computers, especially then with respect to this construction approximation aspect. I mean, we want to control this, if possible, rigorously to get explicit error bounds if we want to put such models on quantum computers where this lattice framework is kind of natural to use. And to relate it to other constructions, so this kind of complements Euclidean imaginary time constructions and the renormalization group methods there, which have a long tradition there. And okay, sorry, so this was related to another talk. So there was on this, I don't know if you know the seminar, so there's this webinar by the Max Planck Institute in Leipzig on quantum fields and probability, and there was a talk by Giuliani on similar aspects on RG methods, so it's kind of left over here, sorry for that. So, but yeah, the idea is to implement some ideas from these Euclidean methods also in the real-time framework. And specifically, I want to talk about how to do this in an operator-algebraic framework. Well, instead of using classical probabilistic methods. So in this sense, it's kind of closer to the construction of the P-phi2 models in the sense of Glim and Jeff, which also use operator-algebraic Hamiltonian methods and directly construct these models in Minkowski spacetime, so in real time. But the RG implementation is a bit closer to, let's say, the work of Balaban, if you know parts of it. And also, as I said, it's natural to connect this with quantum information, quantum simulation theory, and do the connection to quantum field theory via this renormalization group framework. So to give some background on quantum field theory, so of course there are various approaches to deal with quantum field theory, and the approaches which will be kind of relevant to this talk are, on the one hand, ad hoc constructions based on classical field theories or just classical models you can write down. And of course, in real time, you would expect that these classical models are related in some sense in the continuum to field theories governed by hyperbolic partial differential equations, so that you have a notion of causality and propagation, finite propagation speed. And then the quantization of such models usually proceeds by some kind of method of your choice. For example, canonical quantization, where you single out certain subsets of fields or observables of your field theory, which are then subjected to canonical quantization, or you might use a path integral formulation or any other approach you like. But what is kind of common to all these methods is that you need some kind of regularization procedure to tame the number of degrees of freedom involved, and also to kind of handle the tension between locality requirements due to finite propagation speed and the use of quantum mechanical or operator theoretic methods. And to remove this regularization in the end, to achieve an actual continuum quantum field theory, you require some kind of renormalization. And the most general framework here is this, if you want, the Wilson-Kadanoff renormalization group, which also unifies it with certain approaches in condensed matter physics. And then, of course, there are also conceptual approaches based on operational considerations about the quantum field theories you would like to have. They are prominently, you might know this algebraic quantum field theory, which allows for a kind of conceptually clean formulation of what you would expect of a would-be quantum field theory if you constructed it, and where you kind of want to reconstruct the field content from the observable content of the quantum field theory model. And the typical data you have here is that you just assume that there's a kind of net of observables which associates observable quantities to space-time regions. And these observables are then typically phrased in terms of, say, C-star algebras or von Neumann algebras. And their self-adjoint part is then constitutes the observables, and put some additional requirements on these nets, which are typically causality. That's the most important one. So if you have operations or observables associated with space-like space-time regions, which is denoted by the symbol here, then you expect these observables to commute so that they allow for a simultaneous measurement in a certain sense. Then other properties are, typical properties are isotony. So if you increase the space-time region, then of course you only gain additional measurements. But depending on what specific model you're considering, some of these might be violated, but typically causality is the most important one you want to have. And to connect this to actual quantum physics, you typically also require a vacuum state. So a state that has certain invariance properties under space-time symmetries and satisfies spectrum conditions with respect to the energy as the generator of time translations. But of course, there are also possibly many more ways you can approach quantum field theory, but these are kind of the two ones that are relevant to this talk, if you want. And the idea is to combine kind of methods from this algebraic approach and from the more ad hoc constructions to get actual models. And specifically, as I said before, I want to formulate Wilson RG or Wilson Kadanoff RG in the language, in a language which is adapted to this algebraic quantum field theory. And an example will be the construction of the Ising field theory from the transverse field Ising chain. Okay, and so what should this reformulation of Wilson-Kadanoff renormalization be? Well, the setup will typically be the following. So you start from a sequence of models, quantum mechanical models, which are associated with a certain discretization of, let's say, equal time slice of your space-time, and these are kind of effective Hamiltonian quantum systems approximating your ideally approximating your quantum field theory in the end. I call them lattice field theories, and this parameter n here should be related to a kind of scale parameter in the sense, or logarithmic scale parameter in the sense that if you increase n, then you consider finer lattices, which I sketched here. So the idea, like if you look at the square lattice in a plane, you would have, for example, associated observables and local Hilbert spaces to the vertices of your lattice. Of course, you could also associate them to edges or plaquettes. That's not really the point here, but some parts of this lattice are associated with these quantum degrees of freedom, and you have a natural sequence of these models for finer and finer lattices. Yeah, and then the Hilbert space of the total system at a given scale, for example, be the tensor product over all the local on-site Hilbert spaces, and similar for the observables or the basic fields of your theory. And you would have an effective Hamiltonian that governs the dynamics of this discretized system in the sense that it, for example, acts by a Heisenberg-like evolution on the observables. And now the important thing about the renormalization group is that once you're given such a sequence of effective models, in which sense should they, you might ask, in which sense should they approximate a continuum theory? And to define this continuum theory, what you actually want is a kind of link between the models at these different scales, and that's kind of what the renormalization group is about. So you want to provide maps between these systems at different scale, which then in a certain sense define the continuum model. And originally this was typically done in terms of canonical density matrices associated to the Hamiltonian at an effective scale. So you would assume that your Hamiltonian is suitable to form such a density matrix out of it so that it becomes essentially a state on the algebra of observables at that scale. And then you want a map that maps between different scales that gives you links these density matrices at different scales. And so it's a kind of operation on the pre-dual of your bounded operators. So all the density matrices of a certain system at a fine scale to those at a coarse scale. So what you're doing is the kind of integrating out degrees of freedom. So that's what you typically find in physics textbooks when you talk about the renormalization groups. So you start at a certain fine scale, integrate out some degrees of freedom, and end up with a theory on a coarser scale. And this is formalized here by a map of this form, and typical requirements for such a map are that it should be completely positive because you want to map states to states. And it should be trace preserving because you want to preserve the probability interpretation of your theory. And it should have a kind of semigroup property, meaning that if you compose it successively, then that's the same as just going all the steps at once. And in the Wilson framework, this is often expressed, instead of using the density matrices, by using an operation on Hamiltonians. So you coarse-grain Hamiltonians in the sense that these Hamiltonians define density matrices. So and it's kind of roughly equivalent. And after applying such coarse-graining operations, you would call the density matrix or the Hamiltonian as the new renormalized Hamiltonian at the coarser scale. And then you might compare it to the Hamiltonian which you originally had at this coarse scale. And this trace preserving property is then typically encoded in a condition on the partition functions of the system, so that they should be stable under this coarse-graining procedure. Now, to translate this more into an operator algebraic language, it makes sense to go away from this density matrix or Hamiltonian formulation and instead look at the observables. So what you're doing is, or what one could do there is actually just dualize the whole notion. So instead of using these maps between states, which you have here, which go from fine scales to coarse scales, you define the dual map, which links your observables at a coarse scale to the observables at a finer scale. Meaning that what you're operationally doing is you're resolving observations at coarse scales into observations at finer scales. And then the properties via this dualization process are that you still should have a completely positive map. Now, instead of trace preserving, you want to preserve the unit, which is in that case the same requirement. So it's again kind of quantum channel, and you have this semi-group property now in the reverse direction. So if you refine 2 times, then it's the same as going the whole way directly. And now the original coarse graining maps on the states are then basically pullback operations by this fine graining map alpha here. So if you consider the general state space of your algebras at a certain scale, then you can act with the pullback operation via this fine graining map, and that is the original coarse graining equation, and that's what then defines the renormalization group flow. So that's essentially this equation here. So you start from a certain initial state, which is indicated by the 0 here at a certain scale, and then you obtain a sequence of states at coarser scales via pullback through this fine graining operations. And this whole structure is summarized relatively neatly, I think, by the so-called Wilson triangle of renormalization, which is which you can also already find in one of the classical papers by Wilson. So there, so to just compare it with where you start with an initial sequence of Hamiltonians provided for you at each scale you want to consider. You apply these coarse graining operations, which are these vertical arrows, and that gives you sequences of Hamiltonians at all the scales, which are these horizontal lines. And the actual question of what a continuum limit or a quantum field theory is the question of whether you can find this limiting sequence here, which then would automatically have the property of being stable under these coarse graining operations. So it's in this sense a kind of fixed point of the renormalization group. And in this operator algebraic language, the picture is more or less the same. Some additional data. So instead of starting from Hamiltonians, you start from states on the observable algebras at all the scales you want to consider, and then these vertical arrows here are precisely provided by this equation here. They generate these horizontal sequences of states, and to get a continuum limit would then be to ask whether you can find the limiting state here, which again has the stability property under these maps alpha here. And now the nice thing is that, for example, assuming that your alphas are asymptotically multiplicative, if you asymptotically in this parameter n, then you would at the same time obtain an inductive limit in a generalized form of your observable algebras, and this stable sequence here would then define a state on this limit algebra, and that's actually what defines then the continuum limit in the end. So that's what I summarized here. So the construction of scaling or continuum limits, it's then first considering this inductive limit of algebras under this mapping alpha, and also finding a limit point for these horizontal sequences, which are then, because they are constructed via this pullback by alpha, they will automatically lead to limit states on this inductive limit algebra. And then for those of you who know what this means, so if you form the so-called GNS construction for this limit algebra and this limit state, if it exists, that would give you a Hilbert space, a representation of the limit algebra on this Hilbert space, and a certain singled out vector. And that's what defines the continuum quantum system. Yeah. And of course, then you can also ask, okay, what about, so all this consideration was kind of kinematical. So what would you do about the dynamics? Well, the dynamics can then be analyzed in an associated notion of convergence. You know? So you would take the dynamics at a certain scale, restricted to observables at a fixed core scale, and embed it into the limit state and compare it there to a would-be continuum dynamics. And the question is whether you can establish convergence in this case. And so together with Vincenzo, Gerardo, and Jo, I have shown that in particular, if you start from, for example, free scalar lattice fields, which would be one of the simplest examples, that all this works out. So if you do this construction in that case, start from a typically discretized scalar lattice field model, then these limit states actually exist, and they correspond exactly to the states you want to have in the continuum, and the GNS construction for this tuple of the limit algebra and the limit state exactly provides you with the continuum model of this quantum field in the end. And in some more recent work, we have also checked whether this construction works for the, for example, 5-4 model in 2 dimensions, and there's more or less I mean, it works to the same extent as the Glim-Jaffe construction works. And for example, the interacting dynamics in that case can be recovered via such a construction here. And now let me come to the example I wanted to present, which is the so-called transverse field Ising model, which is in a sense one of the simplest models where you would actually expect a non-trivial renormalization group flow structure, in the sense that this model has a non-trivial critical fixed point and should show a phase transition in the language of condensed matter theory. So it's kind of interesting to analyze this because it goes a bit beyond this scalar field example. And the setup there is that we are working in 1+1 dimensions. And so that means that our space-time, our spatial manifold is just the real line, and we take a circle if we compactify it. And the lattice approximation means that we just take a one-dimensional lattice with periodic boundary conditions in that case. So it's a discretization of the circle of length L with a certain lattice minimal lattice distance, which is encoded into this epsilon, and this L here encodes the size of the circle. So in the sense that the product of these two quantities is always the same for any scale n. And we would do the rescaling in powers of 2. So it's relatively convenient here to use, but you can also use other powers if you want. It doesn't have to be 2, but it's easier to write down in that case. So the Hilbert space for this transverse field Ising model, that's just you take for each lattice side, you take a C2 as a Hilbert space, and you take the tensor product over it. And the observables in that case are just it's just the product of matrix algebras, which is the so-called Pauli algebra of size n in this case, or 2n if you want. And it's generated, or the convenient basis for this algebras at each lattice side is provided by the Pauli matrices. And then the dynamical content of this model is provided by this Hamiltonian here. So you have and that's where this name transverse field Ising model comes from. So you have the usual Ising in next neighbor interaction, which is here between spins in the 3 direction, and you have a transverse field in the 1 direction, where these spins couple to. And then since we're working with periodic boundary conditions, you also have a boundary term which ensures that you still have an action of the translations on the circle, or the discretized translations. And in this case, it's for technical reasons, it's convenient to work with so-called mixed sector boundary conditions for those of you who might know this, so the idea is that, I mean, you could use periodic or anti-periodic boundary conditions, but then if you want to pass to a fermionic description of this model, you would end up with mixed boundary conditions for the fermions. So it's easier to start out with mixed boundary conditions for the spins to have a clean model in fermionic language. But yeah, the whole construction does not really depend on this, but it's just simpler for the formulas, although it might look a bit ugly at this point. And this operator here, minus 1 to the f, that's the Z2 grading, or the operator that implements the Z2 grading for this model, which is just a product of all these sigma 1 matrices over all lattice sites, which implements a spin flip. If you think about a state in the basis of this Z direction Pauli matrix or 3-direction Pauli matrix, then this operator just flips the spins at each lattice site in this, with respect to this basis, and that's what introduces this Z2 symmetry for this model. Okay, and now what one would expect for this model, or that's at least what it's classically supposed to happen, is that if you take the continuous, this model is first of all the continuous time limit of the 2-dimensional classical Ising model. Also, if you start with a classical Ising model on a 2-dimensional lattice and take a continuous limit in one of the lattice directions, then that's the model that results from this construction. And now a typical expectation for this model is that you should get field theory, which is the so-called Ising field theory, out of this model, and for certain couplings, especially when the couplings here, the T's, when they are all equal, we expect that the model is critical and that you get a conformal field theory in the limit. Now, to analyze this whole construction of the continuum limit, it's actually useful to employ the so-called Jordan-Wigner transform, which maps the Pauli algebra at a finite scale to an algebra of fermions at the same scale. So it's a transformation that takes this algebra P, which is just this algebra in terms of Pauli matrices, to an algebra of the canonical anti-commutation relations based on the one-particle space, which are just the L2 sequences on the lattice. So I mean, of course, this L2 requirement is not really necessary for finite n, but it's just here to emphasize that when we send n to infinity in a certain sense later on, then this L2 condition is that which becomes relevant to characterize the limit space. And this mapping, I've written down here how it explicitly looks like, and in terms of this mapping, Schultz and Mattis a long time ago have solved this model exactly, and it's a kind of reformulation of the original solution by Onsager. Okay, and since I wanted to discuss the so-called disorder parameter later on as well, so that's a thing which appears when you look at the image of the spin operator in the 3-direction under this identification here. With these fermion operators, so it's so the disorder parameter is this part, or this operator here in terms of fermions. Okay, and now if you apply this Jordan-Wigner transform to the original Hamiltonian, then you realize, and that's why the model is exactly solvable, is that you get an operator which is quadratic in fermions. Either you use Majorana fermions, which are this size here, with periodic or anti-periodic boundary conditions, or you can use complex fermions and takes this form here. And now we want to discuss, or I want to discuss the continuum limit of this model via this renormalization group procedure by implementing this operator algebraic renormalization in terms of these fermions. So it's easier to do it for the fermions than for the spin operators. And now I also want to consider the translation invariant case, which is just the one where all these coupling constants are not really depending on the point. You just get one coupling constant for the transverse field and one for the next neighbor interaction. And you can introduce a so-called lattice mass parameter, which is just 1 minus the quotient of these two coupling constants. Now the finite building blocks, which I want to use in this operator-algebraic renormalization group construction, are now this the fermion algebra at scale n, the corresponding Hilbert space, which is still the same. It's just a product over C2s, but you can reformulate it as an antisymmetric Fock space, and this Hamiltonian here in terms of fermions. And to actually construct the limit, it's also useful to introduce the so-called dual lattice, which results when you do a discrete Fourier transform at each scale, which is then this approximation of the lattice Z, which would be the dual lattice of the circle in the continuum. And the one particle space, as I said before, such as these L2 sequences, tensorize with C2. That's when you use the Majorana fermions, because when you use complex fermions, you can equivalently use Majorana fermions with a one particle space of double dimension. So for those of you who know this, that's the so-called self-dual formalism of Araki. And yeah, the quantum systems, as I said, are the CAR algebra, and the Hilbert space is essentially the antisymmetric Fock space based on this one particle space. And now the scaling limit construction. So let me just go back once more briefly. So here, as I said, what we need as an input here are not only these quantum systems, but also this diagonal sequence of states here from which we generate these horizontal sequences. Then we have to show that these horizontal sequences have sensible limits. And this diagonal sequence, that's one of the input data, and what we use as an input is the ground state of this Hamiltonian. And this Hamiltonian, since it's quadratic, it has a Gaussian type of ground state, which means in the fermionic language that it's fully determined by the two-point function in terms of annihilation and creation operators on the lattice. And that means, this notation here means that the expectation value of the ground state of the product of two of an annihilation and a creation operator is just given in terms of an inner product of the smearing functions of these two operators here, which are just elements from this one particle Hilbert space. And there's a certain one particle operator, which gets used in this inner product. So this is, in a sense, what you find for any of these quadratic Hamiltonians on a CAR algebra system, or on a system using a CAR algebra. Then you will always have something like this, and you have to find this P operator, so this one particle operator that defines the state. And in this case, it can be explicitly calculated. So that's via this explicit solution of Lieb, Schulz, and Mattis. And you find that it's even a projector, which means that the state is pure in the sense of state on a C-star algebra. Okay, and it's computed in terms of the lattice dispersion relation of the fermions and the one particle Hamiltonian, which means which is the operator that gives you this Hamiltonian here via second quantization. So if you take the second quantization of this operator, that gives you the origin, the Hamiltonian of the quantum system, and that's one particle projection operator that defines this state here. And the dispersion relation on the lattice takes this form. So this might look kind of familiar. So you have a mass term. Remember, this lambda n was a lattice mass, and you have something that is a lattice approximation to k square, where k is the momentum or an element of the dual lattice. So here you would formally expect that if you make epsilon small, which corresponds to a continuum limit, and rescale the dispersion relation correctly, then you should actually end up with a massive dispersion relation of a free field theory, and that's what's going to happen. And just one technical remark. So this Hamiltonian at each scale, which we start out, this is a so-called self-dual Hamiltonian, in the sense that it has a certain commutation property with respect to a conjugation operator on the one particle space. And so if this psi is a one particle vector, you can define a conjugation on the one particle space, which is just the usual conjugation of the entries of the vector, and then you also apply a rotation to it. And this Hamiltonian commutes in a suitable sense with this conjugation operator, which is necessary for it to be realizable in terms of Majorana fermions. And now it's also useful to do a chiral decomposition in a sense, which means that since at criticality you expect that this corresponds to a conformal field theory, this model, so there should be kind of decomposition of the theory into left and right moving fields, which in the Euclidean language would correspond to having holomorphic and anti-holomorphic parts of the continuum model. And you can, to some extent, already mimic this at the lattice level, and it's convenient to do this to obtain the actual limit. And the conformal symmetries you would then recover in the at criticality. They are related to this chiral decomposition. So you get two copies of the Virasoro algebra in the continuum limit, and one of these Virasoro algebras acts on, or each acts on one of the chiral components of the theory. Okay, and this decomposition is essentially of this form here. So you define this one particle projection operator in terms of the Pauli 2 matrix. That projection operator is compatible with this conjugation operator, and it defines a decomposition of the one particle space into the chiral and anti-chiral part. Okay, now conformal symmetry, as I said, would be expected at the critical point, which is in this case the mass, this scaling limit, so where you require that this combination, so the lattice mass rescaled by epsilon, that it actually goes to 0 in the limit and to infinity. So you can view this as a kind of renormalization condition. So the only parameter of the model, in a sense, is this lattice mass, and requiring it to have a sensible limit when it's rescaled in this form, that's a renormalization condition. And if you condition it to be 0, then you're actually talking about the critical model. Okay. Now the most important point to construct the limit is how should we implement this renormalization group, which, as I mentioned before, is phrased in terms of these maps alpha, which take you from a coarse scale to a fine scale. And it should be provided in terms of a map between the fermion algebra on a coarse lattice going to the fermion algebra on a fine lattice. And here we use some ideas which already work for the scalar field example. So we start out from something which is called a compactly supported orthonormal scaling function. So if you don't know what it is, don't worry. So the thing is that it's just a function on L2 in L2 on the real line, which satisfies this identity. So it has the property that it can be at unit scale, it can be decomposed into itself, rescaled by a factor of 2. And these rescale and these coefficients here that are used in this decomposition, they are called low-pass filter. And in certain cases, or there are examples for these functions where you can actually have finite sequences. So where this low-pass filter is finite, and this equation is the so-called scaling equation, and it's a well-known thing from wavelet theory. And a typical example, so I've put 2 examples here. So the first example is consider just the indicator function of the interval 0 to 1. Then you can decompose it, of course, into the rescaled function on half the on half the unit interval with a certain factor, and then it will satisfy this equation. But this function is not very nice because it doesn't have very good smoothness properties. So of course it's even discontinuous. So the question is, can you improve on this? And might not look very nice, but actually these functions have very nice properties. So they are the so-called Debussy wavelets. And one example, so which is like in this Debussy sequence, it's the next highest order after this so-called H wavelet of this indicator function. That's a function which has a kind of fractal structure, but it's at least continuous, and it has some fractional derivatives. And this has the property that now if it's defined on an interval of size 3, and you can decompose it into 4 times itself, rescaled by a factor of 2. And the coefficients for this rescaling are even known analytically. And it's a general fact from this wavelet theory that you can achieve any degree of smoothness you want, provided you increase the support of the function you want to have. But you can never get a smooth wavelet with finitely many coefficients. So you can get arbitrary orders of derivatives you want, but a smooth function is only possible if the sequence H is infinite. But for the considerations or for the constructions we want to make, it's actually sufficient to have enough derivatives. So we can work with compactly supported functions and finite sequences of H. And now we can use these coefficients, so such a low pass filter here, to define isometric mappings on the one particle space. So this psi is a function from the one particle space at lattice scale m. And we embed it into the lattice at scale n by such a construction here. So what we do is we decompose the function, or we redistribute the coefficients of the coarse lattice onto those of the finer lattice by basically using this low pass filter here. And this has even a nice asymptotic form. So if we want to embed such a one particle vector into the continuum Hilbert one particle space, which would be the space of the L2 functions on the circle, then it's just a kind of discrete convolution with the scaling function in terms of this Hn. And now we get these alpha maps by essentially second quantization of these one particle isometries. So they act on annihilation or creation operators that constitute the fermion algebra by simply acting on the one particle vector associated with this thing. And the good thing is that because of choosing finite sequences here, these scaling maps are actually compatible with locality or anti-locality in this case, so anti-commutation relations of the fermions. Okay, and now one can show that you can actually do this operator-algebraic renormalization procedure to define the inductive limit algebra, and that's in this case because the wavelets associated with, so there's a certain basis of L2 on the circle associated with these scaling functions. That's a so-called wavelet basis constructed from the scaling function. And since this wavelet basis is dense in L2, the basis, you actually get that the inductive limit algebra constructed from these alphas is just the CAR algebra on the L2 functions on the circle, and in the sense that the Hilbert space, the inductive limit of the one particle Hilbert space is just this L2 space. And you can also show, and that's the more important part, that this limit of renormalized states converges for any fixed scale m you start from, provided you enforce a certain renormalization condition, namely that the limit of this ratio here goes to a constant, to a positive constant. And then what you find is that the limit state has the following two-point function. So it's completely characterized in terms of this asymptotic map, which contains the scaling function and a limit of this one particle projection operator, which can be explicitly computed, and that's this one. where now this omega mk is really the continuum dispersion relation you would expect for a massive field, where this mass here is really the enforced by this renormalization condition. And that's that shows, so of course you might not see this directly from this expression, but this is really the one particle projection operator you want to have for, or you would want to have for a massive fermion in the continuum. So the scaling limit construction really tells you that in this sense, the scaling limit of the transverse field Ising model gives you a massive fermion in the continuum. So because now you have this limit state, and by this general considerations from the beginning, you can now use this limit state to define a projective limit state on this inductive limit algebra, and the GNS construction with respect to this pair really gives you the algebra, gives you the Hilbert space and the representation of the massive fermion in the continuum, which is precisely the one of the massive fermion that you would expect. Okay, and now, since we are already close to 3 o'clock, let me maybe just briefly also comment on the conformal symmetry and the disorder parameter. Yeah, so what I showed you so far is that you can reconstruct this fermion field theory from this transverse field Ising model, but the fermion model, in a sense, is not the full object you would want to have for the scaling limit of the Ising model, because the fermion only coincide with the even part under the Z2 grading of the Pauli algebra. So you would have to reconstruct also the spin operator itself, which is an odd operator under the Z2 grading, because basically the sigma 1 anti-commutes at each lattice point with the sigma 3 operator. So it's odd under this grading. And so what we would actually want to do additionally to reconstructing this fermion is showing that there are certain odd operators under this grading, which we can also obtain via the scaling limit procedure. And for example, to construct the spin operator, one ingredient that's necessary for it is the so-called disorder parameter. So the reason for this is, so let me go briefly back to the beginning. I illustrated this. So here, see that in terms of fermions, the spin operator, which is this sigma 3, is the product of the disorder operator and the fermion operator. So if we are able to construct the disorder operator, then this would allow us to also get access to the spin operator, just in terms of fermions and the disorder operator. And that's something we understand to some extent how to get it, but that's not completely finished yet. And then, as I said, another point is the reconstruction of conformal symmetry. And here, let me just mention, so there is a formula that has been proposed by Ku and Scalar, which gives an explicit proposal how to approximate these the Virasoro generators, so the generators of conformal transformations in critical quantum lattice systems. And the reasoning behind that is essentially that you can start from the so-called Hamiltonian density of your would-be field theory. That's a combination of the stress energy tensor and its conjugate. And if you look at the Fourier transform of this Hamiltonian density of your would-be field theory, then that would formally correspond to a linear combination of Virasoro generators, or generators of the local conformal transformations. Then you can play around with these formulas and you get a formula for this LK in terms of the Fourier transform of the Hamiltonian density. This formula can, by analogy, directly be translated to the lattice model, whereas in input you use the Hamiltonian lattice density and then do its lattice Fourier transform. And that's essentially this formula here. And it's a formula proposed by Ku and Scalar. And so with Tobias, I've shown that in this context of operator-algebraic renormalization, we can actually show that this formula converges to the Virasoro operators of the limit theory at criticality. So when the mass of the fermion model is 0. And yeah, maybe I skipped this part here. So this is just the algebraic reformulation in terms of these chiral parts of the theory. So remember, each of the chiral parts would carry a representation of the Virasoro algebra. So we can restrict the state which we have at each lattice scale to these chiral parts, and we have also a certain explicit formula there. And we do these operator algebraic renormalization with respect to now these chiral parts separately, and that's where we show convergence. And then yeah, so the idea of how to show convergence is basically sketched in this box here. So what we would have is we have these approximations of Virasoro operators at each scale n. We use these asymptotic maps, which are defined by the inductive limit construction, to map these operators to our inductive limit algebra. Then we use the representation of the scaling limit state to get a representation in the continuum limit Hilbert space. And there we can compare the action of this operator at finite scale with the actual one. Yeah, so with the Virasoro operator in the continuum, which we know how to construct for a free massless fermion. And the convergence that we show is that essentially on a dense common core of these operators and these, you can take the limit n to infinity, and that actually goes to 0. So that's the convergence statement we would have there. And yeah, I just wrote this down here. So in terms of this wavelet-inspired renormalization group formulation, that's kind of what you get. So here we compare the action of the discretized ones embedded into the continuum with the actual ones, and on certain finite particle number vectors which are constructed via this renormalization group maps. So that's vectors from this domain here. You get the convergence. And alternatively, you can also use momentum cutoff renormalization group maps, which are slightly different than these wavelet ones. And then you would also get this statement here for representations where you have a central charge non-zero. So in the relevant case of central charge equal to 1 1/2 for this fermion. And moreover, here we consider the Virasoro generators for indexed by these dual momentum vectors, but we can also consider smeared versions of these Virasoro generators, which would be linear combinations of this type here. And via this, you can localize them in real space. Yeah? So you can get real space, opposition space, local conformal transformations. And if you pick these approximating sequences in such a way that they are convergent in certain Sobolev spaces on the circle, by the conditions you would need here are given in this paper by Carpi and Feiner, then you can even show that these operators, these smeared out operators, would converge in this sense. Yeah? So you get the same statement, just replace this LK here with such an L of X. And then by the usual techniques, like Trotakato theory, you get from the convergence, from the strong convergence of these generators of local conformal transformations, you also get the convergence of the associated unitary groups and the associated Heisenberg dynamics of these conformal transformations. And yeah, combining all this, you can also get results for the approximation of correlation functions. Now you have sequences of operators in these algebras on the lattice, and you can look at dynamical correlation functions, and they will also converge by these theorems. And you get them for the fermions, but also for correlation functions of the Virasoro net, if you want. Yeah? So the operators generated by local conformal transformations. Okay. And yeah, so as a comment maybe on this quantum simulation aspect, so the nice thing here is that each of these these finite scale models, they have a natural realization on would-be quantum computers, provided we can get sufficiently many error-controlled, error-corrected qubits. But then, because this Ising model is essentially directly given in terms of qubits, so like a C2 on-site or vertex Hilbert spaces, each of these finite scale models has a direct realization on a quantum computer, so can be implemented. So in this sense, these statements directly tell you how to approximate a conformal field theory or a quantum field theory on a quantum computer. And what is not stated here is that we also get explicit error bounds for this convergence. So we can estimate how far, in a sense, these discrete correlation functions are away from their continuum ones. And typically the error scales like s squared, where s is the size of the lattice, this is the total size. So in the sense that this renormalization group approach even gives you direct error control for such would-be simulations. And yeah, another comment is that we can also extend this argument to so-called nonabelian currents, so certain current operators that would appear in Wessel-Minor-Witten models, which have also a reform or can be formulated in terms of tensor products of free fermions. So those would be analogous to these Virasoro operators, slightly different form. And yeah, for those things, the same approximation results hold. Well, okay, that was it.
Okay, thank you very much for your talk.
Mm-hmm.
Questions? So from the online participants. Maybe would you like to explain again this OAR regularization technique a little bit?
Yeah, so any more specific things you want to understand, or so maybe I go back to the general setup.
Yes, with Wilsonian.
Yeah, so so the main idea here is that I mean this was like this sketchy overview of what happens in the Wilsonian framework, where you, I mean, in a sense, you could say, I mean, if you want to character or phrase it in terms of like quantum mechanical language, so the Wilsonian approach is a kind of Schrödinger picture of renormalization, in the sense that you consider the action of the renormalization group on states of the system, and or via this correspondence with these canonical density matrices, you could also say you consider the renormalization of Hamiltonians. Yeah? But if you look at the original papers of Wilson, then what he actually starts from is not the Hamiltonian, but he starts from the canonical density matrix, basically because that's one of the typical ensembles you would choose in the statistical mechanics approach. So in this sense, it's based on states. And of course, as we know, we can also dualize this picture. So instead of looking at coarse graining of states, we would look at the fine graining of observables. And these three properties here, they are just the kind of minimal requirements you would want to have from a, let's say, quantum information perspective on such coarse graining operations. So this complete positivity, maybe I should slightly elaborate on that. So, I mean, complete positivity basically means that you can tensorize your system with arbitrary many identities, if you want, and still have the same properties for the map. And in the sense of, in statistical mechanics, that would actually, or in quantum statistical mechanics, that would correspond to the idea that you can consider your system as a subsystem of something larger. So requiring complete positivity essentially means that it does not matter whether this is your whole system or just a subsystem of something else. So you can also take in a sense, you can also take the thermodynamic limit. It's kind of compatible with that. And yeah, as I said, the trace preserving property essentially means that probability is conserved. So your new coarse grained density matrix has still basically covers or has probability 1 if you just do no measurement. And yeah, so in a sense you don't lose any information. And in this dual picture, that so what I mean here by the dual channel is just, if you think about the state given in terms of the density matrix, then evaluating the state on an observable means that you just take the trace with this density matrix and an observable. And the dual channel is just the one where instead of acting on the density matrix, you dualize with respect to the trace operation, and that gives you a map on the observables. But now this goes in the other direction if you want. So in BERT's sense, all the arrows, but complete positivity is a property that is still preserved here and also makes sense in this picture, because you want to consider your observables as maybe a subsystem of something larger. In that sense, that would be realized by just adding identities on the sides where you're not doing anything. And complete positivity of this alpha means that it's compatible with this. And unitality again means, okay, if you start from, if you take the unit in a small system or in a coarse system, which is like the no observation or just doing nothing, that's still the same in the finer system. And then the semi-group property is just a kind of coherence property, which is maybe the one you might not necessarily want to impose. So it would be sufficient that this holds asymptotically, in the sense that for large m and n, this property should hold. So I mean, there's the theory of generalized inductive limits also, so where you don't enforce this equation exactly for finite m, n, and k, but just approximately in norm. And then you could still form the corresponding limiting object. So that could be sufficient here, but yeah, for computational reasons and because it works here, why not use it? So, but you could relax it. And in a sense, these are the minimal requirements. And in the specific example of the Ising model, all this is a bit, I mean, the alphas have even more properties. In that case, they are star morphisms between the algebra. So since all star morphisms are completely positive and they are unital by construction, so you get all these properties, but even stronger ones. So it makes life a bit simpler. But the main intuition here is that you have observables associated with a coarse lattice. So in this picture here, for example, think of making an observation just at this lattice side here. And then, of course, if you want to think about this observation in terms of the finer lattice, it's not so, you have to resolve it into the observables on the finer lattice. Then you could claim, okay, it's just again the observation at the same lattice point, just viewed as a part of the finer lattice, but it could also be a combination of the neighboring ones, which were not there at the coarse scale, and that's what's realized then later on explicitly in terms of these low-pass filter coefficients here.
No.
So that basically means, okay, do an observation here at this lattice point, but it might just correspond. So where the next lattice point is actually at 3 here, if you want, or no, at 1. But what this means here using the low-pass filter is that this observation at the coarse lattice is actually decomposed into observations at these finer lattice points. And then the morphism properties, they follow from, or this complete positivity, unitality, that all follows from specific properties of these wavelet coefficients.
Mm-hmm.
But in a sense, you could already guess from the scaling equation that which, I mean, this kind of encodes the same philosophy here. So you have scale, you have the function associated with a point x, but since this function satisfies this identity, you can also think about a sufficient number of copies of this function scaled to a smaller size, and that provides you with the same information. And that's kind of the same idea here. And yeah, so that's about the construction of these maps. And well, the general procedure, well, that was this triangle here, is that's kind of the idea of how we want to think about a scaling limit or a continuum model. And well, basically it was Wilson's idea that what you should do to characterize such a limit model is you provide yourself with these diagonal sequences, which are Hamiltonians or density matrices or states for each fixed scale you have. So you basically, that means this n sets your observational scale. You want to be free in choosing the observational scale, so you need a model for each scale. And to get a continuum limit, you want to construct out of these initial models a sequence of models which is actually consistent under this refinement operation or this coarse graining operation. And that's constructed in the sense that you just do this coarse graining operation and then try to find the limit points of this. And something, okay, I should comment this, so that's kind of hidden in this picture. So each of this Hamiltonian would have a set of coupling constants, which are also dependent on the scale you're at. So that's how the usual picture of renormalization of coupling constants comes in. Namely, doing the coarse graining gives you a new Hamiltonian, which has possibly new interaction terms, but also new coupling constants. And the existence of the limit here is tied to also choosing conditions on these couplings such that the limit exists. So because only in very specific cases, you don't need to do any adjustments of the couplings, that would precisely be the fixed points of the renormalization group flow. So in a sense, this horizontal line is really the flow of the renormalization group, and only at fixed points, you don't need to impose conditions, you just get a limit. But everywhere else, to get a continuum limit, you need to impose these conditions. And in the specific model, there was only one coupling constant, which was this lattice mass. And the critical one is where the lattice mass is 0, and then you see, okay, you get a limit without doing anything because you fixed it to 0. But in all other cases, you need that the lattice coupling, which was this lambda, which was this one here. So the lambda depends on n, and it has to go to 0 at the rate set by the lattice scale. Or not to 0, but to get a massive theory, essentially the rate at which this goes to 0 is set by this mass parameter here. So in this sense, that's a kind of condition of how the lambda n goes to 0 in terms of the lattice scale. And the rate is what is setting the physical mass in the end. And the additional thing here, and that's I think what's kind of nice about this operator-algebraic formulation. So in the Wilson picture, you would have to talk about convergence of Hamiltonians in some space which you do not even specify in the usually. So maybe you want a kind of Banach space of interactions and do some fixed point theory there, but that's usually very hard. But here it's, I mean, in this operator algebraic language, it's a bit simpler. I mean, of course, you don't get things for free, but at least this formulating what you're doing is kind of easier. You have these elements of the state space, but each of the, I mean, if these, for example, are C-star algebras as in the model, then your state space is compact. You just consider at each scale, just have an action by pullback of these maps alpha on the compact state space, And then, for example, because of the, weak star compact, but the pullback action is, of course, compatible with the weak star topology. So you have an action of these maps alpha in the right topology in which the space is compact, so you're at least provided with the existence of limit points, for example. And then the enforcing renormalization group conditions really just means that you, from your bounded sequence in the space of states, you just select certain cluster points. So in this sense, at least the flow itself is defined on a suitable object. And you also need, and in a sense also for free, you are given the algebra just by this inductive limit construction, which still has the drawback that it might not contain all the fields you're interested in. So this algebra is basically a set of basic fields you start from. So in this transverse easing model case, it's the fermions. But there might be other fields like the spin, which you also want to have, and they need to be reconstructed in terms of these fermions in the end, which is the part you don't get for free. Okay.
Thank you.
I would have maybe one other question. Is there, in principle, some obstacle to develop this theory in higher dimension? Or
well, you can formulate it in higher dimensions, but of course you encounter all the difficulties that the other approaches have. That typically these quantum fields are, the singularities you expect for these operators, they increase with the dimension, and this is what shows up in actually determining the limit of these states in some sense. So there's no principal obstacle in formulating the approach in this way, but you're not avoiding difficulties. That would be strange. It somewhat gets, you don't get a free lunch if you want.
And, would it imply some solutions for a 3D Ising model, or is it? Would it be implied on the other way around by when somebody solves the 3D Ising model where the critical points are, would it be helpful for this, or?
Yeah, sure. If you would find exact formulas for, let's say, correlation functions at criticality, then yes, that would be helpful. Yeah. So in a sense, all the approximation problems you obtain in other approaches, for example, if you think of the 5-4 construction in 2 and in 3 dimensions, then one difficulty in 3 dimensions compared to 2 dimensions is that you have way less control on the ground state, if you want, of the model. So even showing that the 3-dimensional 5-4 Hamiltonian is a self-adjoint operator is already problematic. So in this sense, you have a conservation of difficulty. But if you end up with a formula for certain ground state correlation functions that is amenable to this rescaling procedure, then that might be indeed helpful to carry out the limit.
And one other very short question. I didn't get on the last slide where you said you can consider non-abelian currents. What do you mean by non-abelian?
So the idea there is that so there are these if you want loop group models in terms of these Wilsonian models, and there you have certain current operators. So current operators means you basically have things that can be expressed in this. In these models, you can express them in terms of quadratic expressions, in terms of certain fermion fields, and they are structurally similar to these Virasoro operators. So maybe this helps a bit. So if you look at Virasoro generators in this limit of the transverse Ising field and the associated fermion model, then you will find that they are actually second quantized operators in terms of one particle operators, which means that they have the form that they are kind of linear combinations of A dagger, A dagger, A dagger, and AA. So you just have quadratic expressions in the fermion operators. And for these Wessel-Minowitten models, you can also find certain operators, these currents, which have this form. And the main difference is that you get a kind of, you have a different one particle operator, which contains then certain matrix valued functions as well, which take values in the Lie algebras associated with these loop models. So in this sense, they are non-abelian. Yeah? So if you compute commutators between these currents, the structure constants of these groups pop up. But for these objects, basically the same approximation results hold.
Okay. Okay, thanks.
Okay.
I think we may have no more questions from our side.
Okay.
So, thank you very much. Another round of applause for you.
Yeah, thanks a lot for listening. And
yes. Okay, so stop the recording and
okay.